As per IS 456-2000 consideration, we know if the ratio of longer span and shorter span is less than 2, then we have to design the slab as two-way slab, as I have discussed in previous video. So in this video, I am going to design two-way slab directly. So let's read out the problem first. Design a RC slab for a room of clear dimension 4 meter by 5 meter. The slab is supported on walls of width 300 mm. The slab is carrying a live load of 4 kN per meter square and floor finish 1 kN per meter square. Use M20 concrete and Fe 415 steel. The corners of slabs are held down. So before starting the problem, I am going to discuss the basic part of two-way slab. We know that in two-way slab, bending comes in both sides. So we have to design reinforcement for longer span and shorter span both. There are no such as distribution bar. There are a torsional moment come in the corners. So in corner there are torsional reinforcement have to be designed, and for both sides, that means for longer span and shorter span, we have to design reinforcement for middle strip only, and for 4 edges we have to provide edge strip as per IS 456-2000. The total consideration of two-way slab is given in Annex D of IS 456-2000. So let's have a look to Annex D IS 456-2000. This is Annex D of IS 456-2000. Slab spanning in 2 directions. So these are the consideration. We will read it out when we will solve the problem. That will be easier to you to understand the clause and the consideration. There are 2 figures also. In page number 90, we can find this of IS 456-2000, and next page, table 26 also needed for this design. So let's start to solve the problem. Ly by Lx is equals to 5 meter by 4 meter. Ly is longer span, that is 5 meter given in question, and Lx is shorter span, that is 4 meter, that is also given in question. That is equals to 1.25. So this is less than 2. That means this is a two-way slab. We have to design the slab as two-way slab. Let's assume L by D, length to depth ratio, is 25. From this assumption, small d, effective depth, is 4000 by 25, that is 160 mm. Now assuming clear cover as 15 mm and using 8 mm dia main bar, so overall depth will be effective depth as per assumption, that is 160, plus clear cover, that is 15, plus half the diameter of main reinforcement bar, that is 4. So overall depth is 179 mm, or we can say 180 mm. Now effective depth is equal to overall depth 180 minus clear cover plus half dia, that means 15 plus 8 by 2 is 4, that is equals to 161 mm. Next step is span consideration. As two spans of two-way slab is in consideration, so we have to find out effective span in x direction as well as in y direction also. But we have to consider effective span as per clause number 22.2 of IS 456 2000. Look, simply supported beam or slab, the effective span of a member that is not built integrally with its support shall be taken as clear span plus the effective depth of the slab or beam, or center to center of support, whichever is less. So, as per clause, the effective span in x direction, either center to center distance, that is equals to 4 meter, the clear span of length of shorter span, plus 0.3. This 0.3 meter, that means 300 mm, is the width of wall, that means width of support, which is given in question. So that is equals to 4.3 meter, or clear span plus effective depth. So clear span is 4 plus effective depth as per calculation is 0.161 meter. So that is equals to 4.161 meter. From these two, the shorter, the lesser will be accepted. Therefore, effective span is equals to least of the above, that is equals to 4.161 meter. Similarly, the effective span in y direction Ly is equals to 5.161 meter. So now we have to design the load, which is denoted by WU, U for ultimate. So self weight of slab is equals to 0.18 into 1 into 25, that is 4.5 kilonewton per meter. 0.18 means 180 mm, the overall depth we have considered, multiplied by 1. 1 is, we know slab is always designed as 1 meter width of beam, and 25 is unit weight of RCC. So self weight of the slab is 4.5 kilonewton per meter. Floor finish load is given 1 kilonewton per meter. Now floor finish load is given 1 kilonewton per meter square in question. So 1 into 1, that is equals to 1 kilonewton per meter. Now live load is given 4 kilonewton per meter square in question. So live load is 4 into 1, that is 4 kilonewton per meter. This one multiplied with finishing load and live load is 1 meter width, which is in consideration. So total load will be 9.5 kilonewton per meter. Now we have to multiply load factor, that means partial safety factor for load, the combination of dead load and live load, which is we can get from table 18 of IS 456 2000, that is 1.5 for the combination of dead load and live load. So factored load will be 9.5 into 1.5, that is equals to 14.25 kilonewton per meter. This is factored load. So next step is design moment and shear. For this step, first of all, we have to get the knowledge of Annex D IS 456 2000. So let's check it out. So where is Annex D of IS 456 2000? As per clause number D11, the maximum bending moments per unit width in a slab are given by the following equations: mx for shorter span, is equals to alpha x w Lx square, and my, moment for longer span, is equals to alpha y w Lx square, where alpha x and alpha y are coefficients given in table number 26. We will just go through table number 26 after this. W is total design load per unit area. Mx and My, moments on strips of unit width spanning Lx and Ly respectively, and Lx and Ly is effective lengths of shorter span and longer span respectively. So let's check table number 26. So formula for moment in shorter span, mx is equals to alpha x w Lx square, and for longer span my is alpha y w Lx square. Let's check table number 26. So table number 26 is bending moment coefficient for rectangular panel supported on 4 sides with provision for torsion at corners. So table number 26 is given for bending moment coefficient for rectangular panels supported on 4 sides with provision for torsion at corners. In the table, in most left column, number 1 case number is given. Then second one from the left is type of panel and moment considered. So there in this column the support conditions are given. As per support condition, coefficient of moment will change. There are total 9 types of support system. In next column, short span coefficient, that is alpha x. There are few values of Ly by Lx. Depending upon the value, the ratio of Ly Lx, the value of alpha x will change. And in last column from the left, that is long span moment coefficient, that is alpha y, for all values. The alpha Ly Lx value is not the criteria for this, only support condition is the criteria. So these values are given for these support conditions. So there are many support conditions like interior panels, one short edge continuous, one long edge discontinuous, two adjacent edges discontinuous, two short edge discontinuous, two long edge discontinuous, 3 edge discontinuous, 4 edge discontinuous, etc. If any condition among these is directly or indirectly given in question, we will go through these values depending upon Ly Lx value. If any condition not given in question, we have to consider any condition among these 9 conditions. Okay. So generally we consider, if not given, if support condition is not given in question, generally we consider the number 9, 4 edge is discontinuous. Okay. So let's go to the problem. So in this case, support condition is not given in question. So we may consider the slab is supported on all the 4 sides and its corners are held down as given in question. Therefore, we have to consider